Welcome, I'm Bruno Berenguer Baeta from the Research Group of Robotics, Perception and Real-Time in the University of Zaragoza. I'm going to present our paper titled Floor Extraction and Door Detection for Visual Impaired Guidance. This article starts with the objective of helping visually impaired people. According to the WHO, in 2020, 36 million people were totally blind. Classical methods for guidance or navigation of visually impaired usually need long periods of adaptation. Learn how to use a white cane or train a guiding dog can take several months or years. New technologies and research can provide new methods that reduce this adaptation time to a minimum. The last decade, many approaches have been proposed in order to help visually impaired people. One of these approaches is the use of sensors placed in an environment, monitoring the user's position and guiding him in these environments, avoiding the obstacles. The main problem of this approach is that it can only be used in indoor environments with a correct setup. A more flexible approach is the use of wearable devices. Different sensors are attached in a device that the user can carry wherever he or she goes. This allows to move in different environments. In recent years, the reduction of price and size of cameras has made them the main sensor in many navigation applications. The possibility of using these cameras in wearable devices, united with the great development of computer vision algorithms, has increased the applications for navigation where different types of cameras are used. In this paper, we propose a perception system which uses two different cameras, and we have also developed two different algorithms to help in the navigation in unknown environments. The algorithms proposed are a floor extractor in order to find the obstacle-free paths in the environment and a door detector to move from one environment to another. Besides, we have performed some experiments in order to test the proposed algorithms. We also propose a navigation solution based on these algorithms. Our perception system is the combination of two different cameras, an RGB-D camera and a fisheye camera. With the RGB-D camera, we can directly obtain 3D information from the environment. However, it is constrained by this narrow field of view that goes from 40 to 60 degrees. On the other hand, with the fisheye camera, we have a wider field of view of around 180 degrees. However, we cannot obtain 3D information of the environment. Combining both sensors, we aim to obtain 3D information in a wider field of view. With this information, we will have a better understanding of the surroundings of the user in the environment. In order to use the proposed perception system, we need to know the calibration of the cameras. The intrinsic calibration parameters are computed with different projection models. For the RGB-D camera, which is quite similar to the conventional perspective cameras, we use the pinhole camera model. On the other hand, the fisheye camera presents big distortions, so we need to find a different projection model. In our case, we use the Scaramuzas model for revolution symmetry cameras, which gives good calibration results for fisheye cameras. The extrinsic calibration parameters relates the cameras among them. For our perception system, we will use the method proposed by Perez et al., which allows to obtain the extrinsic calibration parameters of a set of cameras if at least one of them is an RGB-D camera. The first algorithm that we propose is a floor extractor. This extraction is made in two steps. First, we aim to detect where is the floor in the image and to obtain the plane equation. Second, we extend the information in the environment. The floor detection is made with the 3D information provided by the RGB-D camera. We implement a ransack in order to extract the main plane of the point cloud provided by the RGB-D sensor, which, due to the orientation of the cameras toward the floor, this main plane will be the floor plane. After the ransack algorithm, we get the plane equation of the floor, which will allow us to make measurements. However, the information of the detected floor is constrained by the narrow field of view of the RGB-D camera. So we extend this information with the wider field of view of the fisheye camera. To do so, we need to change the camera reference from the RGB-D camera to the fisheye. This change of preference is made with extrinsic calibration parameters computed before. Once the floor information is in the fisheye camera reference, we will proceed to extend the information. Since the fisheye camera we only have the color information, we need to find a method to extend the floor with only the color. For that objective, we use a seeded region growing algorithm. This algorithm takes an initial seed and extends this seed into other regions. However, instead of making a pixel-by-pixel comparison to grow this seed, we segment the image in superpixels that cluster the pixels with similar color into bigger regions. The initial seed of the SRG algorithm is the floor information obtained in the RGB camera. This information will overlap some superpixels in the fisheye image, which will be defined as a base floor. We also compute the color histograms of these superpixels and save them as reference. Once defined the initial seed and the reference histograms, we will still computing the color histograms of the adjacent regions. The new regions will belong to the floor if the color histograms are similar. If that does not happen, the growing in that direction will stop. After the SRG algorithm stops, we make an extra verifications. Since the horizon line is always above the floor plane, any pixel defined as floor which is above this line will be deleted. With this implementation, we can extend information from the RGB-D camera many times, obtaining better results to plan trajectories in the environment instead of just avoiding obstacles. The second algorithm that we propose is a door detector. This algorithm takes as prior the segmented floor from the previous algorithm. Then, after a line extraction where we only kept the vertical lines, we propose a structure of hypothesis generation and verification to detect the doors. The hypothesis generation is made in two steps. First, from the vertical lines, we made two different hypotheses. First hypothesis is that two lines separated at distance can form a door. And the second hypothesis is that one line can be part of a door that is at one of its sides. From this hypothesis, we generate colored seeds. Then we roll the colored seeds with the same SRG algorithm proposed before. Here we assume that the doors have a uniform color that is different from the walls and the floor. The colored region resulting from the SRG algorithm are our door hypotheses. The hypothesis verification is made with three constraints. These constraints are quite restrictive in order to avoid false positive. The first constraint is made through a cross ratio. This taking measurements of the hypothesized doors and comparing the result from real doors, we can reject those hypotheses where the hypothesized region is too different from the real door. The second constraint is the distance of the hypothesized door regions to the floor plane. Ideally, this distance should be zero. With this constraint, we reject door-shaped objects as windows or frames. The third constraint is only for the one-line hypothesis, since we do not have a measure of the doorway. Here we compute the aspect ratio of the oriented bounding box of the hypothesized color region and compare this aspect ratio with that of real doors. The hypotheses that fulfill this constraint are verified as doors in the environment, while the others are rejected. So once presented our perception system and the algorithms for floor extraction and door detection, we have performed a set of experiments to test these algorithms. Then we will propose a navigation solution using the proposed perception system and the algorithms. Experiments have been made with a prototype device where the cameras are placed over the user's chest and the computation unit, in our case a laptop, in a rucksack. The tests are performed in different environments where the ground truth has been labeled manually. Here we show some examples of the floor extraction experiments. We present results from different environments, indoors as well as outdoors, and in different illumination conditions. In the video on the right, we can see the different steps in the floor extraction. In the top right, we have the floor information provided by the RGB-D camera, while at the bottom, the floor extension in the fisheye image. We present the numerical results from the floor extraction. We can observe that the precision and recall is quite high. Besides, if we compare the floor area obtained from the RGB-D camera and extended using the fisheye camera, we observe that the extracted area with a combination of cameras goes up to 20 times the extraction with only the RGB-D camera. This will allow to create trajectories in the environment instead of just avoiding the obstacles ahead. Here we show some examples of the door detection experiments. In red are the results of door detection from the two-line hypothesis, while in yellow are the results from the one-line hypothesis. And here we present some numerical results of the door detection. We observe that around 50% of the doors are detected. This low number is due to the hard restrictions in the verification process, since we want to avoid any false positive detection, which has been achieved. So once seeing the experiments, We make a navigation proposal using the algorithms and perception system proposed. We divide the space around the user in 5 different sectors, which at the same time are also divided in 5 distance sectors. We define the obstacle-free space in those sectors that coincide with the extracted floor. Besides, since we have the floor plane equation, we can obtain the distance to the closest obstacle in each direction. At the bottom, we present an example on how the navigation system works in an environment. After the floor extraction, the sectors that overlap the floor are defined as free space and notify the user via voice commands. In conclusion, we have presented a new perception system based on 2 different cameras and 2 algorithms to extract key features in the navigation of robots and visually impaired people. We also propose a navigation system that can be used in different environments. Besides, due to the wide field of view, we can plan trajectories in these environments instead of just avoiding the closest obstacles. So here concludes our presentation. Thank you all for your attention.